Right, let us look at the concept of eigenvalues and eigenvectors. So if you are given such equation, a times x bar is equals to lambda times x bar. A, it is your matrix, a given matrix, which is a square matrix, n by n. X bar is your eigenvector, and your lambda is your eigenvalue. Given an example here, I've written a matrix 555 where your A, it's that matrix, your x bar, it's the 1 1, and your lambda is 10 and 1 1, right? So this is just an example, the picture that you are going to have, right? If you are trying to understand it deeply, you need to understand that whenever you have a matrix here, right, you have that matrix, you have this vector and vector v1, which is 1 1, right? And if you take this vector here and multiply it with this function, this matrix here, what will happen? This vector will be elongated at the same line. By how many units? By 10 units. So v1 prime, it's the same vector, it's just now it elongated, it's going to be 10 10. So you need to understand that eigenvectors and eigenvalues, this is what it does in a particular matrix, right? How can you find the 10 10 1 1 and the tens? So let us have the equation again. Ax is equals to lambda x. Now if you're trying to solve for lambda, because you first need to find your values of lambda to solve for the eigenvector. So this is what is going to happen. You're going to take this part to the other side. So I'm going to have ax minus lambda x is equals to 0. What you need to know is that lambda is just a constant. Lambda is just a constant, and these two are actual vectors. So to simplify some stuff, what you need to do, you need to make x the subject, or you need to take out x as the highest common factor. So I'm going to have a minus lambda times x is equals to 0, right? And what we're going to do, we are just going to say two conditions, right? Two conditions that this thing will happen. Now for x bar, need to be a non-zero vector. So we need x bar to be a non-zero vector for this thing to work, right? For this thing to work, we need this thing here to be a non-zero vector. So we have something which is called a non-trivial solution. We have a non-trivial solution. And for x bar to be a zero vector, then we have a trivial solution, right? We have a trivial solution, but we are going to focus on a non-trivial solution. Now let us proceed from this equation. So what I'm going to do, I'm going to take the determinant of a minus lambda is equals to 0. But there is a problem here. There is a problem, a big problem, because A is a matrix and the lambda is a vector. Just remember that A is a matrix and the lambda is just a a constant. So in this case, you have a matrix A like A, B, C, and D minus lambda. You cannot subtract these two things here because they have different orders. Because A is a 2 by 2, 2 by 2, and lambda is a 1 by 1, you cannot add them. But what we can do, we need to multiply this thing here by an identity matrix to add it. So by what do I mean by that? I'll have something like this. I'll have A, B, C, D minus lambda times 1, 1, 0, 0, 1. Because if you multiply this thing, if you multiply lambda by an identity matrix, actually I'm not changing anything. I'm not changing anything. So by multiplying by the identity matrix, I'm making sure that I can add these two things here. I can add them. So what will happen? I'll have A, C, B, D minus lambda 0, 0, lambda. Remember, this lambda here will multiply each entry inside that identity matrix to have such format. Now you can add these two matrices, right? So here now I'm going to have the determinant of A minus lambda in is equals to 0. It's going to depend to the order of matrix A that n is going to be. So for a 2 by 2 matrix, so I'm going to have I2. For a 3 by 3 matrix, I'm going to have I3, right? It's not always going to be a 2 by 2 matrix that I'm going to multiply lambda. It's always going to depend on the matrix A and its order to have that, right? This thing, the determinant of A minus lambda in is equals to 0. It's called the characteristic equation. It's called the characteristic equation, right? Right, it's called the characteristic equation, right? So it's going to help you to find the determinant of it's going to help you to find the eigenvalues of a particular matrix, right? So let us look at an example. No, we're not going to look at an example, but we're just going to focus on the characteristic equation, right? Now what you'll have after finding the determinant of this thing, we will have a polynomial of degree same as the order of a matrix. We are going to have a polynomial. If you're going to simplify this thing, we are going to have a polynomial of a degree same as the order of a matrix, right? If you're trying to find the eigenvalues of a 2 by 2 matrix, so I'm going to have a polynomial that will start with lambda square. If you are finding the determinant, if you are trying to find the eigenvalues of a 3 by 3 matrix, you are going to have a polynomial starting with lambda cubed and so on, right? So let us look at the polynomial. For a 2 by 2 matrix, I'm just only going to do for a 2 by 2 and a 3 by 3. Your characteristic equation characteristic equation is given as follows. So it's always going to start with a positive lambda square minus the trace times lambda plus the determinant of matrix. you are trying to find the plus the determinant of a matrix that you are trying to find the eigenvalues for. This is always the case, right? And for a 3 by 3 matrix, right, the characteristic equation is given as follows. It's given as follows. It's given as follows as positive lambda cubed minus the trace lambda squared plus the sum of minus in the diagonal lambda plus the determinant of a matrix is equals to 0. So this is the characteristic equation of a matrix. So this is the thing that you need to follow to find the eigenvalues. And for eigenvectors, to find the eigenvectors, we need to follow the row operations, or we need to perform something called the row echelon form. We need to perform the row echelon form, right? So this is the theory behind on how to find the eigenvalues. This is just the theory, right? I'm just going to do 2 examples on how to find the eigenvalues and the eigenvectors, right? Only 2 examples, actually 4. Yeah, actually 4 examples. Let's change that to that. Let's change black. Let's change it to this one, right? So find the eigenvalues and eigenvectors, right? So let us try to find the eigenvalues and the eigenvectors. So for A, let me just give you a matrix A, which is 5, 5, 5, 5. Let us try to find the eigenvalues. To find the eigenvalues, I need to say the determinant of A minus lambda I2. Why is it I2? Because the order of this matrix is a 2 by 2. So we need to find I2. And the next step that you need to follow must be this step. The determinant of 5 minus lambda, 5, 5, and 5 minus lambda is equals to 0. Whenever you're trying to find the eigenvalues, you're always going to subtract your lambda in the main diagonal. You're always going to find you subtract the eigenvalues in the main diagonal. So it's always like that. And then after this, you need to find the determinant of this matrix. Finding the determinant of that matrix, I'm going to have 5 minus lambda times 5 minus lambda minus 25 is equals to 0. Now you can waste your time now to simplify the thing, but what you can actually do, you need to follow this rule here because it's a 2 by 2. So first I'm going to start with lambda squared minus what? Minus the trace of a matrix. So we need to minus the trace. So the trace of a matrix, it is when you add the entries in the main diagonal. So it's 5 plus 5, which is going to be 10 lambda, and then we need to find the determinant of this matrix. Because the rows are equal and the columns are also equal, we will say that the determinant of that matrix is 0. You can try to find it by yourself, but the determinant of this matrix is 0. So this thing is equals to 0. And then if you factorize lambda, I'm going to have lambda minus 10 is equals to 0, and now I'm going to have lambda 1 is equals to 0 and lambda 2 is equals to 10. So always the first lambda must be the smallest and the second lambda must be the biggest. So lambda 1 is equals to 0 and lambda 2 is equals to 10. Right. So some university prefer that you study how to find the eigenvalues, but some will actually want you to find the eigenvectors. Now, if you know that you want to find the eigenvalues, you can just skip until you find me trying to find an eigenvalue of another matrix. But for those who are trying to find the eigenvectors also, this is the procedure. Right, to find the eigenvalues, you need to remember this formula actually. AX bar is equals to what? Not AX bar. This formula that says lambda, not lambda, sorry guys, sorry. It's actually A minus lambda in times X to give you 0. Because what I'm just going to do, I'm going to substitute lambda to this equation here and multiply it by the column vector and equate it to a null matrix. So this is the procedure. So I'm going to have, if we substitute 0 in that equation, I'm going to have 5, 5, 5, 5 times, this is always the case, x1, x2 is equals to 0, 0, right? 0, 0. And then find the two systems of equations. But you can notice, I love it when you guys stuck on how to find the eigenvectors. If you can notice, this row and this row are actually the same thing. Because those two rows are actually the same thing, I said when we did linear dependence and linearly independent, we said that the first row is depending where? The first row created the second row, right? So because the second row is depending on the first row, I am going to let this last entry of x2 to actually give me alpha. I'm just going to let it to be alpha, because these two, we have two equations which are the same, right? We have two equations which are the same, and they give us the same answer, and we are expected to solve these two equations to give us x1 and x2. Because row 2 is created from row 1. Row 2 actually is called a free row. Because that is a free row, it's going to correspond with the second variable, which is called as a free variable, which is alpha. A free variable is created when a row is depending on the other row. Since row 2 is depending on row 1, which means row 2 is the same thing as x2, we will say that x2 is alpha. And then to solve for x1, we need to write the top equation or the second equation. So we are going to have 5x1 plus 5x2 is equals to 0. But we know that x2 is alpha. I'm going to have 5x1 plus 5 alpha is equals to 0 to the other side, and then x1 is actually negative alpha. Right, x1 is negative alpha, so v1 is actually negative alpha and alpha, and then your v1, it's negative alpha is equals to 1, negative 1. Always know this. Always know this. You need to understand that an eigenvector is a vector of any variable. of any number, right? It is a vector of any number. But our university prefer that your first entry is positive and it's not a fraction. You must not have fractions on the eigenvector. You must always have whole numbers, and you need to have your negative down, not in the first entry, which means I took out negative alpha as the highest common factor because your eigenvector must not have a negative on the first entry. It must have negative on the other entries down below, right? I think that seems clear. And the next thing that you need to do, we need to find the eigenvector for lambda 2. To find the eigenvectors for lambda 2, what I'm just going to do, I'm going to take this 10 and substitute it in there. Substituting that 10, I'm going to have 5 minus 10, which is negative 5. 5 minus 10, that is negative 5, times, remember, we need to have a standard. A standard that we have is that we need to multiply this by x1, x2, and equate it to 0, 0, right? To equate it to 0, 0. And then after equating to it 0, 0, you can notice that we have row 1 in this matrix and row 2 in that matrix. And to get row 2, you need to multiply negative 1 on the first row. Can you notice that? To get row 2, you need to multiply negative 1 on the first row. In that case, we'll say that row 2 is a free row because it's depending on the first row. And then this x2, I'm just going to let it to beta. I'm just going to let it to beta. You can also let it to alpha, but I'm just making things different, right? So I'm going to let it to beta. And then if x2 is equal to beta, try to solve the system. So I'm just going to use any row as a system of equation. So I'm going to choose row 2. So x1 minus 5x2 is equals to 0. We know that x2 is beta. 5x1 minus 5 beta is equals to 0. To the other side, x1 is actually beta, right? In that case, so v2 is actually beta. Take out beta as the highest common factor. Beta is 1, 1. So in this case, you can notice that your v2 is actually 1, 1. That is your v2. And for v1, it's 1, negative 1. Right? This is the procedure to solve the eigenvalues for a 2 by 2 matrix. Let us look at another example on how to find the eigenvalues of this matrix. Right? The first one, the second example, it's this matrix B 2, 3, 3, 2. Actually, some of you know that the transpose of this matrix is actually what? The original matrix. Because if you take the transpose of B, you're going to get the same matrix, really. It's called what? A Hamilton matrix. I cannot remember really. Skew matrix or symmetric. It's a matrix in that format. So what we need to do now, we need to find the determinant of this matrix. The determinant is equals to B minus lambda I2 is equals to what? Is equals to 0. Right? This is the matrix that you will get. This is the matrix, that is the equation that you need to do. And then after this, you need to say the determinant of 2 minus lambda, 3, 3, 2 minus lambda. You're always going to subtract lambda from the entries in the main diagonal. And what next? You need to find the determinant of this matrix. So I'm going to have 2 minus lambda times 2 minus lambda minus 9 is equals to 0. And then trying to simplify this, you are going to try to simplify it, but you know that you are going to say this is lambda square minus the trace of that matrix lambda times the determinant. So it's 4 minus 9, which is minus 5, is equals to 0. And if you factorize this matrix, I'm going to have, lambda minus 5, lambda plus 1 is equals to 0. So lambda 1 is equals to -1, or lambda 2 is equals to 5. So these are the eigenvalues of this matrix. Alright, and then now we need to find the eigenvectors, the corresponding eigenvectors for these two matrices. To find the corresponding eigenvectors for these two matrices, what you can actually do, you can start with lambda 1 and end with lambda 2. So to find the eigenvalues, or to find the eigenvectors of this matrix, you need to remember this formula. You need to take this lambda and substitute it back here. So now I'm going to have 2 minus 1, but I'm going to have a 3, 3, 3. 2 minus 1, that is a 3 again, multiplied by what? The standard. The standard is what? It is x1, x2 is equals to 0, 0. You're always going to multiply by that part. Right, you know now that these two equations are actually the same, and the first row created the second row, right? We have the row 1 here, we have the row 2 here in that matrix. So row 2 is a free row, it's going to create a free variable. So I'm going to say that x2 is equals to alpha, and then it's going to be 3x1 plus 3 alpha is equals to 0. In that case, x1 is equals to minus alpha. So v1 is actually minus alpha, and v1 is negative alpha 1 minus 1. You know that we need to take out the highest common factor of minus alpha, because in a matrix, we cannot, in an eigenvector, we cannot have a negative value as a first entry. Right, so I think you got that. And the next thing that you need to do, we need to find the eigenvalues, the eigenvectors of this 5. So substituting 5 to this equation, where you say lambda, I'm going to have a negative 3, 3, 3, negative 3, times what? Times the standard, which is x1, x2 is equals to 0, 0. Right, now again, you can notice that to get the second row here, we have row 1 here, we have row 2. To get the second row, though, you need to multiply the second row by what? You need to multiply the first row, by -1 to get row 2. In that case, row 2 is depending on the first row. If in that case, then we can say that x2 is equals to beta, and then use any row or equation to solve that. So I'm going to have 3x1 minus 3 beta is equals to 0. And try to solve for x1. x1 is actually beta, and your v2, it's going to be beta, beta, b2. So your final equation that you're going to have it's going to be beta 1, 1, like that. So that is the eigenvalues and the eigenvector of a 2 by 2 matrix, right? So let us try to look for the eigenvalues of a 3 by 3 matrix. Right. So, right, let us look at example C. For example C, let us have this matrix. Let us have 1, 0, 0, 3, 4, 3, 8, 7, 2. Alright, is equals to 0. Not equals to 0. Just a matrix. Alright. Let me just remove this tree for now. I'm just going to tell you something at the end about what are the eigenvalues of this matrix. Let me just tell you now. The eigenvalues of such matrix, are the entries in the main diagonal. So you have this number, and that number as the eigenvalues of this matrix, but we'll see at the end. So to find the eigenvalues of this matrix, we say the determinant of C minus, because it's matrix C, of lambda I3 because the order of this matrix is 0. So then we're going to have the determinant of 1 minus lambda 0, 0, 3, 4 minus lambda 0, 8, 7, and 2 minus lambda is equals to 0, like that. So those are the eigenvalues, or that's the characteristic equation. And then remember, to find the determinant in a 3 by 3 matrix, you use any row or any column that you are going to have. So if you notice, this column has most zeros, so use that column to find the eigenvalues. So if you use that column to find the eigenvalues or to find the determinant, I'm going to have 1 minus lambda times the submatrix 4 minus lambda 0, 7, 2 minus lambda is equals to 0. And then if you proceed by simplifying this, I'm going to have 2 minus lambda is equals to 0, because 2 times 0, 0 times 7 is 0. So you see that lambda 1 is actually 1, lambda 2 is actually 2, and lambda 3 is actually 4, right? So whenever you have a matrix in this form, whether we have this lower triangle here, this lower triangle there, your eigenvalues are the entries in the main diagonal, right? So now we need to find the eigenvector. To find the eigenvector of this matrix, we will start by finding the eigenvector for lambda 1 and finding the eigenvector for lambda 2, right? So how can we do that? We're going to do the same thing for what is this, for the 2 by 2. We're going to do the same thing that we did in the 2 by 2 to get the thing on the 3 by 3. So let me just grab my calculator because I don't have it on my side. Right, now I have it. Now, because we need to do row operations, yeah? So let us try to find the eigenvectors of this matrix. So for lambda 1, it's going to be a long process, but bear with me. For lambda 1 is equals to 1. What I'm just going to do, I'm just going to say, okay, this is the matrix. Subtract 1 to every term there. Subtract 1 on the lambdas, so I'm going to have 0, 0, 0, 3, 3, 0, 8, 7, 1. Times what? Times x1, x2, x3 is equals to 0, 0, 0. Now, this is the first case that you need to know when solving the eigenvectors of a 3 by 3 matrix. You need to understand when you solve for a 3 by 3 eigenvectors for a 3 by 3 matrix, you are trying to solve for x1, x2, x3, and this thing is given as an equation because your last row here has a 1. What we are going to say, 1 times x3, which is x3 is equals to 0. Now we know that x3 is equals to 0. Because x3 is equals to 0, we are left with 2 rows. We are left with 2 rows, right? In those 2 rows, we are going to have 2 equations. So because x3 is equals to 0, I'm just going to say, what? This thing is confusing here. I'm just going to say let I'm not going to let x2 is equals to 0. Yes, I'm going to let x2 is equals to 0 if I may. If I say let x2 is equals to alpha, let x2 is equals to alpha, I can able to solve for, I'll be able to solve for lambda in that case, for x2, right? Let x2 to be alpha. So for the second equation, I'm going to have 3x2 plus 0 is equals to 0. Now, we are trying to solve for x2. Oh Lord. Right. Yeah, x3 is equals to what? x3 is equals to 0. Which is 0.